Big Data Analytics Overview. In this section, we will define what big data is. We'll also establish the reasons why so much data is being generated in the marketplace. We'll look at why traditional database technologies or traditional supercomputer technologies don't really work for solving big data problems. We'll also look at the philosophy behind some of the new approaches and the technologies that have come into place in the marketplace that make it possible for us to use new approaches for solving big data problems. And then we will look at big data analytics, which is a technology that many companies are embarking into so that they can get insight into their big data. And there's a new field called data science coming up in the marketplace in support of big data analytics. Unless you've been living under a rock, you've heard of data. To be precise, you've heard of big data in the news. Science magazine talked about data. Time magazine talked about your data for sale. What they really mean is how companies like Facebook, Google, Twitter are actually using your data to make money. And then there is also the Economist magazine talking about data deluge. Believe it or not, there is something called too much data. There is a data diet. There's all kinds of different things that's happening in terms of how to reduce the volume of data, how to generate information out of the big data. So there's the data deluge. In other words, the fact that Science magazine, Time magazine, and Economist magazine is talking about data, to be precise, big data, means there's something major that's taking place in the marketplace. Before we define what big data is, let's define what is data. So in order to do that, I went to the Merriam-Webster dictionary and looked at the definition for data. It said factual information as measurements or statistics. I think we all understand this. Basically, if you represent a customer, if you represent a transaction, if you represent an item in a database, that's factual information. That would be pretty straightforward definition of data. There's also another definition that they gave, which is information output by a sensing device or organ that includes both useful, irrelevant, or redundant information. The classic example that I can think of this is the Internet of Things that's coming up in the marketplace, where a temperature sensor is keeping track of the temperature and sending the current temperature periodically to some kind of a centralized server. Now, it's useful information, but it's also redundant information because the same temperature may be being sent for the next 5 minutes every second. It may be irrelevant information because after 5 minutes, after 10 minutes, the information may not be valuable anymore. So that's also another definition of data. And then there's a third definition of data that Merriam-Webster dictionary gave, which is information in numerical form that can be digitally transmitted or processed, which is really taking data representing in some kind of a digital format and then sending it over the network to some other location and processing it. And if you really think about it, that's really the definition of data. Okay, so how does it connect to big data? Well, let's define big data. Big data is when data set becomes so large that you have issues collecting the data, storing the data, organizing the data, analyzing the data, moving the data from one location to another location, and also sharing that data. Big data, another definition is data whose scale, distribution, diversity, and/or timeliness requires the use of new technical architectures. It's really important to understand, requires the use of new technical architectures. So the definition of big data is when you cannot really solve that data analytics problem using traditional technologies, because you need new technologies that allow you to distribute the data, allow you to scale the data processing, and also there is so much data, there's so many different kinds of data that need to be processed in a timely fashion. So the idea here is that it requires new data architectures, analytics sandboxes, new tools, new analytical methods, and you may have to integrate multiple skills and may have to even create a new role of a data scientist. All these things are part of the definition of big data. The reality is that the data volumes are growing. Here I've represented data, to be precise, big data, as an iceberg, because if you really think about it, An iceberg, although is massive, the real mass of the iceberg is really at the bottom, under the water. The point I'm trying to make is we're already seeing the beginnings of big data, but there is even more data to come. So big data is going to become a very important industry going forward. Let's look at data creation. Here's an eye candy or eye chart that describes how data is being created in the internet space. This chart visually illustrates how much data is being generated per minute. In a minute, about 571 websites are being created. In a minute, over 2 million searches are taking place in Google. In a minute, 3,600 new photographs are being shared by users at Instagram. In a minute, about 47,000 apps are being downloaded. 27,778 new posts are posted at Tumblr. As you can see, there's a lot of data that is being generated within a minute. All this data needs to be processed and analyzed to make sense out of. And by the way, this chart is from 2012. These numbers are probably growing dramatically if you look at a similar chart today. Let's look at why so much data is being generated in the marketplace today. Let's compare the 1970s with today. In 1970s, when people built applications, they built applications for about 2,000 online users at most. For example, when people built applications at AT&T to be used by the employees of AT&T to take order in the 1970s, they built it for about 2,000, 3,000 users to be online who will take your orders. Today, 2,000 users is the starting point for any application. You build your application, you deploy it online, you get about 2,000 users to start with, but if your application becomes popular, let's say you deploy it in Northern Virginia, suddenly your application is being accessed by the entire Virginia, and then your application is being accessed by the entire East Coast, and then West Coast, the entire United States, and then it goes to Europe, Asia, Africa, Australia, and now you've gone global. That's a global user population. So in the 1970s, you dealt with static user population. Now you're dealing with a dynamic user population worldwide for your application access. In the 1970s, people built applications for business process automation. For example, at AT&T, they built applications for their employees to take in orders from the customers whenever you wanted to order a telephone line. Today, customers want self-service. So it is also business process automation, but it's for customers to access their data, customers to access their billing, customers to self-provision. For example, today, users want to go online, make the bill payment themselves online. They want to move money online, transfer money online, all by themselves logging into a banking website, or maybe even using a mobile phone device or mobile phone app. So it's business process automation, but self-service. More users are using it. Highly structured data records where what was being stored in the database. Today we are dealing with structured data, unstructured data, and also semi-structured data. What do I mean by this? Structured data is really your data that has structure, your traditional databases. Semi-structured data is more along the lines of XML and JSON objects that are coming up. Unstructured data is images, video files, PDF documents. So different kinds of data are present today that need to be processed and analyzed. In the 1970s, data networking was at its infancy. Today, universal high-speed data networks are quite common. In the 1970s, people did centralized computing using mainframes and mini computers. Today, it's all about distributed computing. You have lots of large, highly powerful computers that are computing with each other using high bandwidth networks to send data and process data between the machines. You also have your mobile phones that are connected to the internet, always connected, and they're sending data back and forth. So distributed computing from that particular angle too. So there's a lot of data being generated because there's a lot of devices that are coming online, and there's a lot of users that are coming online. Now let's look at data in an enterprise. In an enterprise, you have existing OLTP databases. Many organizations have many OLTP databases that represents different products and the different customers. that those products may be consumed by. The organizations also have user-generated data. Many organizations have blogs and tweets that they themselves blog and tweet, their customers blog and tweet that they want to process, video files, audio files that need to be processed. There's also log information. There's logs that are coming in from all these different web servers or from all these different application servers that may have to be processed. There is also system-generated data. Companies may have lots of different kind of systems, and those systems may be generating data. They are monitoring data, and that needs to be processed. So there's a lot of data within an enterprise that need to be processed. You don't have to be a company like Facebook or Twitter to be a big data company. Even normal organizations, because of their computing power, because of the kind of different databases that they have within their organizations, because of the different log files, because of different systems that are generating the data, they need big data solutions too. What are the characteristics of big data? There are actually 3 V's that are associated with big data. One is volume, which is really when the volume of data that's coming in is on the rise. Many companies are seeing a lot of data that's coming in. For example, Facebook is seeing a lot of data that's coming in. Facebook has lots of people that are putting their updates, that are posting images. So there's a lot of volume of data that's coming in. Same thing with Twitter. There is also velocity. Velocity is when the data is coming in at a very, very fast rate. It may be coming in for a very short period of time, but it's coming in at a very fast pace. For example, when you have American Idol asking people to vote, that may be 50, 60 million users that are going to be voting in the next half an hour or an hour. That's a lot of votes that are coming in within a very short period of time. That's velocity of data. And then there is also variety. Variety is when there's lots of different kinds of data that need to be brought in and processed. For example, a company may bring in data from relational databases, may want to bring in video files, may want to bring in PDF documents, may want to bring in tweets, may want to bring in blogs, and kind of put it all together and try to make sense out of that. That would be the variety of data. So whenever you have any one of these things in your data system, you can consider to be a big data system. Just because you have lots of data, volume of data, just the fact that you have volume of data. It may not be velocity, it may not be variety, just volume, just one fact out of these 3 facts. If it is true in your data set, then you can consider to be big data. Some people may just have velocity. Some people may have variety. Some people may have velocity and variety. You get the idea here. There are several traditional technologies that exist in the marketplace, but the reality is those traditional technologies don't really work. For example, supercomputers in the 1970s and 80s were really an array of servers with fast connected interconnect. But they don't really work well because, first of all, they're too expensive. They use proprietary technology, and also they work for fast computation. They do not work for big data. They're really great when you have some data and that needs to be processed heavily across multiple machines, not big data. Big data requires distributed storage. They don't really do distributed storage. Relational databases. Relational databases really use a single server with attached storage for storing and processing data so that they can honor ACID properties. Now, the reason relational databases don't really work because they cannot handle big data, because all the data has to be stored in a single machine. It has to be processed by a single machine, a single storage, a single machine, because they have to maintain the ACID semantics. So that's not going to work. And also, it doesn't work when it comes to unstructured data. It's not very easily possible to store data such as video data and audio data and process that. It doesn't really have the right tools to process that kind of data within a relational database. So relational databases also don't really work. The reality is that all data cannot fit in a single machine and all processing cannot be done on a single machine. The philosophy behind distributed computing was well said by Grace Hopper, a computer scientist and Rear Admiral in the Navy. She said, in pioneer days, they used oxen for heavy pulling. And when one ox couldn't budge a log, they didn't really try to grow a larger ox. We shouldn't be trying for bigger computers, but for more systems of computers. In other words, what she's saying is what we really should be doing is not go for larger and larger computers with more and more memory and more CPU. We should really be going for computers that are moderate or mid-sized computers, but many of them working together. So big data processing requires distributed storage, that is storing data across multiple disks, and distributed processing, which is really processing the job across multiple machines. So for big data processing, scale is very important. Whatever system we choose for big data processing, it has to be an economical system. It has to be a distributed system. There are several modern computing trends that are helping big data processing. For example, we are getting faster processing CPU and more memory thanks to Moore's law. Every 18 months, we are getting faster CPU and more memory within a computer. Storage has become cheaper. Organizations are generating a lot of data, but organizations are also storing more data, and the storage has actually become cheaper. Think about the storage in your own personal experience. It used to cost $100 to store 100 gigabytes worth of data. Today, for $100, you can store a terabyte worth of data. Distributed system design has matured in the last 10 years. The Hadoop movement and the NoSQL, which is distributed database movement, have matured. There is also prevalence of open source software. In the last 20 years, the open source movement has taken place. All the developers from all over the world are sharing their knowledge in distributed processing and working together to build complex software rather than proprietary software. More and more commodity hardware is coming into the marketplace. So we are getting into systems of commodity servers rather than those supercomputers. We're also getting into this era of public cloud computing, this elastic computing, this computing as a utility service, where companies like Amazon, Google are providing cloud options where we can grow on demand. So all these things put together are allowing us to do big data processing much better today in the modern world. Big data is affecting every industry. It's affecting the biotech healthcare industry. It's affecting the linguistic industry. Here's a link to a YouTube video. You may want to watch this. In this video, there's a professor who actually records every minute of his child's life from the day the child is born until the child is 5 years old to see how the child learns language. Fascinating video. You may want to watch that, and how they are actually using big data processing to process all the audio data. Mining industry is using big data technologies. Finance industry is using big data technologies. Journalism industry is using big data technologies. Even education is changing. They're using big data technologies. There's also big data technologies being taught in the marketplace so that you can be a data scientist. What are data-driven organizations? A data-driven organization is an organization that acquires data, processes the data, and leverages the data in a timely fashion so that they can create efficiencies in their systems, iterate and develop new products, and navigate the competitive landscape. Well, what does that mean? What that means is many organizations are now jumping into the big data bandwagon, and they are calling themselves data-driven organizations. They are using data to generate new products. So who are these data-driven organizations? If you think about it, companies like Google, Facebook, LinkedIn, Twitter, Bitly, they're all pure data-driven organizations. What are they really selling? What products do they have? It's all data. Search, $35 billion industry, is all about collecting data, processing data, giving the right search results, data back to the customer, back to the user. Facebook is taking your data. LinkedIn is taking your data and sharing the data. So they're all about using the data to provide new services for their customers. They are pure data-driven organizations. Then there are organizations that use data to augment their business. Companies like Amazon.com, which is really a retail site, actually uses data in order to offer a better service. For example, you may have seen the recommendation engine. If you try to buy a product, they'll tell you, hey, you may want to buy this other product too. That's because they are taking all the different data sets of the different people that have bought different products, combining it and trying to get insight into it and helping the customer to buy other products, or even you can look at it as they are trying to upsell, selling other products in their ecosystem. Same thing with Netflix. If you look at Netflix, I don't even select any movies in Netflix. They just tell me what movies I should be watching because they are actually collecting all information about all the users as to what data, as to what movie they are watching, and then making recommendations on what movies they should be watching. In the same way, many other industries are using big data. IRS is using big data for fraud analysis. Lots of companies are using big data analytics technologies in order to improve their business or create new products. That leads to this new field of data science. What is data science? Data science is using multiple data elements, which means different data sets, in clever ways. You kind of pull information out of it, organize the data differently to solve iterative data problems that when combined achieve business goals that might otherwise be intractable. So data scientists are engineers that are able to look at the data, process the data, combine different data sets in order to give you insight, in order to give the organizations insight as to what they should be really doing. The classic example is how Netflix uses recommendation as a mechanism to keep you interested, to give you new movies that you may want to watch, right? There are lots of examples like this in the marketplace. So what does a data scientist really do? Well, a data scientist actually uses a whole bunch of languages. They use Java, Python, Shell, Perl. They use distributed computing technologies like Hadoop, HDFS, and MapReduce. 4G languages, fourth generation languages like Pig, Hive, R, SQL. Machine learning technologies like Mahout and Weka. And also visualization technologies like Gaffle, HighCharts, D3.js, MATLib, in order to make sense of the data. A data scientist is somebody who knows how to gather data, standardize the data, do statistical analysis, modeling, visualize the data, tell a story. These are people that have technical skills like data gathering, standardization, statistics, modeling, and visualization, but they also have some soft skills like curiosity, intuition. So these are all skills that you should have in order to be a data scientist. Now let's look at traditional data analytics versus big data analytics. In traditional data analytics, you're dealing with clean data. Whereas in big data analytics, you're dealing with clean data, of course. You're dealing also with messy data, noisy data. When I say messy data and noisy data, you're dealing data from weblog files. You're dealing data from IoT, which is Internet of Things devices, your temperature sensor, your heartbeat sensor, your pressure sensor, all those different sensors that are sending you data, and they may be sending you redundant data. In traditional data analytics, you're dealing with terabytes worth of data. In big data analytics, you're dealing with petabytes worth of data. In traditional analytics, you often know in advance what are the questions that are going to be asked, and so you actually organize the data in such a way that you can answer those questions through queries. Whereas in big data analytics, you often don't really know what the question that the business folks are going to ask you. So you really cannot design your data in a way so you can answer those questions, which is true in traditional data analytics. In traditional data analytics, you design your BI, which is business intelligence or database or data warehouse solutions around the questions that are being asked. In traditional data analytics, your architecture does not lend for high computation, whereas in big data analytics, you need distributed storage and computation. In traditional data analytics, the typical answers are factual. In big data analytics, typically the answers are probabilistic. What is the probability that this particular person is going to get into an accident? For example, Progressive is actually using data from your vehicle to figure out what is the possibility that you're going to speed and get into an accident, because they are actually installing these small devices in your car and getting all the information about the speed of the car, when the car is being driven, so that they can give you better price. If they think that you're a good driver, they will actually give you a better price. So lots of things are happening in the marketplace in terms of big data analytics, which is actually coming to the customers as products. Again, in traditional data analytics, you're dealing with structured data, whereas in big data analytics, you're dealing with structured and unstructured data. In traditional data analytics, you're dealing with 1 to 2 different domain data sets, which is the variety of data, whereas in big data analytics, you're dealing with dozens of data. Now, let's look at traditional data analytics from a slightly different perspective. In terms of hardware, traditional analytics, you use proprietary hardware, whereas in big data analytics, you use commodity hardware. In traditional analytics, the cost is high because you're using proprietary hardware and software, whereas in big data analytics, you're using commodity hardware and also open source software. In traditional analytics, you typically scale up by adding more and more CPUs and by adding bigger memory, whereas in big data analytics, you scale out rather than scale up. In traditional analytics, you typically do batch processing, which is very slow, whereas in big data analytics, you can do batch or real-time processing, and you want it to be fast processing. In traditional data analytics, you do summarized data and so summarized reporting, whereas in big data analytics, you want to get into deep data analysis because you have all the data. You can store all the data in your distributed storage, and then you can process them using distributed technologies. In traditional analytics, it's mostly operational data, whereas in big data analytics, it's operational data, historical data, and even predictive data. You want to predict as to what the customer may be doing. Maybe you may want to predict as to what the customer may be doing based upon real-time data that's coming to you. In traditional data analytics, you're dealing with structured data typically. Here you're dealing with structured or unstructured data in big data analytics. In traditional data analytics, the architecture is typically physical, which is physical hardware, whereas in big data analytics, people are using physical or even virtual, which is cloud computing, virtualization technologies, and so cloud computing has become prevalent. In traditional data analytics, it's typically reactive, which is really doing analysis and saying, oh, this is what happened in the last quarter, whereas in big data analytics, it's proactive. It's also sensing and responding using real time. Traditional data analytics is high risk because you're going to be buying this huge processing technology, whereas in big data analytics, it's low risk because you can start small and then grow on demand. In summary, big data is on the rise. There are 3 characteristics of big data: volume, velocity, and variety. And the data is being generated at a high rate because more and more users are coming online, which is the global internet population is coming online, and more devices or lots of devices are connecting online through high-speed networking. Traditional technologies don't really work. Traditional technologies like supercomputers and RDBMS processing technologies don't really work because in supercomputers, they may work with multiple computers, but all the data has to be stored in a single machine and they are actually bringing in the data. So it works great for lots of processing, but not big data. Relational databases works great for asset semantics, but they don't really work for big data processing because all the data has to be stored within the same machine. The philosophy behind new approaches is really distributed storage and distributed processing. And there are different technologies that have come into marketplace that make it possible for us to do that today. In terms of big data analytics, it's affecting every industry. And lots of organizations, which we call them as data-driven organizations, are using big data analytics to get more insights into their customers. And they are actually using data scientists to extract meaningful information from their big data. They use commodity hardware, low cost, scale out, batch or real-time processing technologies on physical or virtual hardware.